I would like to give you a fairly broad overview over the ideas that I have developed in terms of the neurobiological infrastructure that enables that uniquely human capacity for language. Now, here's a picture of my daughter when she was 6 years old, proudly bringing back home her shoelace diploma that you see here. That's something for which you need instruction. You go to school, you have to learn how to do this, and it takes quite a bit of time to exercise it and then do it. This in contrast to at the same moment in time, capacity already communicated by the means of language in quite sophisticated ways. That is, without any formal instruction, our brain enables us to learn a language and command a language that, from a formal point of view, might be quite a bit more complex already at that level than, for instance, doing the action of lacing your shoes. And this indicates that our brain has a certain language readiness. And this is what I call the brain as a Kantian machine. It comes to the world with infrastructure that allows it to pick up this complex skill of speaking and listening to a language. And if we want to look at this from the perspective of neuroanatomy, one of the things that we know from the classical model, which I will take as a starting position, is that if you look at, and there's this marvelous book by Pim Level that gives in much more detail the history of the field, also the history of the neurological contributions to that field from the neurologists in the 19th century, we know that there is not only areas like Wernicke's area and Broca's area that have been claimed to be crucial for language production and language comprehension, but there is, for instance, also the arcuate fasciculus, this trajectory that connects the relevant language-relevant regions in the brain. This is still a very popular model in neuroscience and neurology circles, although I will show that it's not completely correct. But let's focus first on this tract, the fiber tract that connects major important areas in the brain for language. Now, if you do diffusion tensor imaging, and that's one of these modern possibilities that MR scanners allow us to do, namely like image the fiber tracts in the brain, we see that there's a major difference if you do this in human compared to chimpanzee and macaque. This is a famous paper by Willing, where he found that the arcuate fasciculus has a much more extended trajectory in temporal cortex and also like partly a more extended arborization in frontal cortex than we find in chimpanzee and macaque. So this is already one indication of an infrastructure that the human brain provides that might be crucial for the language function, which is connecting different language relevant regions in the brain that are much more extended than in the other species. We now know that this is certainly not the only trajectory, the only fiber tract that's relevant. This is from a paper and a review paper by Ahmad and Katani, based also on diffusion tensor imaging work, where we see that there are multiple other trajectories, like for instance here the ungulate fasciculus that connects more ventral areas that are relevant for language processing. We have also the frontal Atlantic tract that seems to be relevant in order to connect some of the medial frontal areas to like Broca's area and beyond. So we see an increased connectivity profile beyond only the arcuate fasciculus as one major extension of the classical model already. If you look at functional studies, the other thing that we realize now is that the activation is much more extended beyond the classical Wernicke's and Broca's area. Both in the left hemisphere, we see a much more extended pattern of activation in temporal cortex, in addition to Broca's area and adjacent cortex, but also partly in the homolog areas in the right hemisphere. So also at that level, we realize now that the classical model has to be extended, because it's not only Wernicke's areas, not only Broca's areas, not only the arcuate fasciculus that are crucial. There's a much more extended network of brain areas that's at stake. Now, of course, we want to know and we want to identify the different contributions of these areas, for which we need to decompose the language system into its multiple components, because language is in of itself a container term that specifies the overall function that we have in order to communicate by means of linguistic types of information in speaking, listening, reading, and writing. But of course, we have to decompose that system in order to know how it's implemented in the human brain. And that's why we need this kind of models. This is taken from Pim Leeveld's overview in order to see which of these components, how are they connected to the infrastructure of the human brain. Now, in order to do this, I make a distinction between three important components. One is the memory component. The memory component specifies the knowledge that a speaker or listener has acquired during acquisition of his or her native language, or other languages as well, about the words and its like components of the native language. And this knowledge includes quite different aspects. So for instance, you know how the words of your language sound. In most cases, when you have gone to school and learned to read and write, you know how they're written. But at the end of the day, we're not interested in the sounds themselves. We're interested in how the sounds make contact to the meaning of the words and the conceptual information that they point to, in order to be able to communicate the content of the messages. Moreover, we need to be able to represent the syntactic properties of the words, such that I know that the word cow is a noun and moo is a verb, and therefore the cow moves can be said, but not the moo cows. And finally, speaking is one of the most complex motor skills that we perform. I have to instruct in the order of 100 muscles in a very timely fashion in order to articulate the words of my language adequately, and this therefore is one of the most complex motor skills that we perform, especially when you realize how quickly we do this. We can easily produce 2 to 5 syllables per second, and that means that we have to retrieve that information from the database of that is represented in my memory in order to do this adequately at a high speed. So that in of itself might mean that some of these motor programs are pre-compiled for instance, high frequency syllables. Now, we can learn from speech errors some of the organization of these particular elements that we have stored in memory. And that goes back to the work of Rudolf Mehringer, who is the inventor of modern speech error research, who collected large number of speech errors in this well-known book Versprechen und Verlesen, where he says that in contrast to the Freudian speech errors, this is the real interesting type of speech errors. What makes speech errors instructive for linguistics is the circumstance that the clockwork's cover has been taken off in such moments and a view on the cogs is possible. And as Pim Leeveld has discussed this in quite a bit of detail, therefore we can conclude that speech errors are not so much pathological, but they reveal the regularities of the system. Let's take 2 examples here. For instance, so here are a few examples of speech errors where you can see that in this particular case, for instance, the word where the speaker wanted to say reading list, the onset sound of the particular word list already is anticipated when presenting the word reading, and likewise the nucleus of this particular syllable is exchanged with the syllable that need to be produced later on, such that instead of pus pocket we get pos pocket. Now this indicates that, in contrast to what you naively might believe, that words are not retrieved as ready-made packages from memory, but have to be assembled from their segments and their syllabic templates every time we produce a word, and that means that this retrieval process is in essence an assembly process. We know quite a bit in the meantime, based on lots of behavioral studies, but also on ERP studies, how this process is temporally orchestrated and what the different steps are that need to be taken. So for instance, if you would look out of the window and all of a sudden you would see an exemplar of Ursus horribilis, that's this particular like animal, the 3D version of that animal will hit your retina, and in first instance, it will allow you to retrieve the conceptual information that you have about this particular animal. And that's a network of conceptual information such that you know that this is a bear which crawls and it's an animal and is thereby related to other concepts in your conceptual memory representation. Once you've selected this particular item, you then have to, in order to be able to produce the word a bear, which you might want to say to your fellow companion at home, you need to first grammatically encode a particular word such that in Dutch, for instance, it's common gender, but let's say the word sheep is neuter gender and therefore has another article. And these types of information are syntactic information, grammatical information that you need to retrieve in order to, at the end, come up with the right article in combination with the word bear. And then finally, you have to retrieve the syllabic template or the syntactic schema in which the segments have to be inserted in order to produce the word bear. We have found that it takes you roughly 50 milliseconds from including the initial segment into the syllabic frame to the final segment for a word like in the order of a single syllable. So we have been able to track the time course of this process, indicating that indeed you assemble this in very quickly in order to produce that particular word, beer in Dutch, which means bear in English. And clearly, there can be exchanges between the segments and the syllables such that you get these kind of speech errors. Now, but of course, this is only one aspect of the assembly process that happens when we produce or understand utterances. The other one is the fact that we can combine words in often very novel ways. Things that make us create utterances that are not part of our long-term memory, that we create on the fly, and that makes up for the large productive capacity of the human language. And that famously has been claimed by Wilhelm von Humboldt in his quotation that Chomsky and others often refers to, namely, language makes an infinite use of finite means. That is, with the finite set of elements, combinatorial operations allow us to create more complex structures and thereby create the open-endedness of the human language system, which makes it stand out the animal kingdom in contrast to the communication systems of other species. Often, this has been claimed in the more Chomsky linguistic tradition. This combinatorial possibilities are due to syntax. That is, the syntactic rules allow us to combine the lexical building blocks in ways that allow us to create this infinite set of new utterances that makes up for the productivity of the system. But I tend to agree with Ray Jackanoff, who has claimed that it's not only the syntactic machinery that allows us to do the combinatorics. In fact, he argues there is at 3 levels. This is the parallel architecture idea. Not only templates available, but also machinery in place that allow us to combine the building blocks that we retrieve from memory, both at the level of phonology, at the level of syntax, and at the level of conceptual structures. And these 3 levels of combinatorics makes up for the basic building blocks of the human language system, where on the one hand, we retrieve information from memory, and then by this possibility for unification, can combine them in larger structures. And finally, if you look at the organization of the language system, there has to be certain executive control components available that allow us to exert control over the linguistic operations that we perform. And this, for instance, is important when we do turn-taking in conversation, or when we select a target language when we are in different contexts of bilingualism, and also, for instance, when we select the message component that we want to convert into a sequence of speech sounds. So, for instance, we have to determine what to say first and so on. Now, are the functional contributions of the node in the language network when we go back to the classical model. Clearly, the classical idea has been that Broca's area subserves language production and Wernicke's area subserves language comprehension, and that these areas are connected by the arcuate fasciculus. But this idea was already based on the work by Duriv and Karamata in the 70s in phasic patients, shown to be incorrect. So clearly also Broca's aphasics have not only problems in language production, but also in language comprehension. As soon as you take away the kind of contextual constraints that allow them to come up with an interpretation, you see that they have these problems as well. So the idea that I proposed, and that I would like to propose here also, is that the distribution of labor is rather in terms of memory structures that are the kind of memory structures of different types of information that we have acquired during language acquisition that are mainly subserved by temporal and parietal structures, that Broca's area and adjacent cortex is important in order to perform unification operations on this information that's retrieved from memory. And finally, that the dorsolateral prefrontal cortex and anterior cingulate is crucial for the executive control operations in connection to the language operations themselves. Now, one can ask the question, why is it that especially Broca's area and adjacent cortex in prefrontal cortex is so crucial for unification? And there are two reasons why this part of the brain could be accepted in evolutionary sense for this functionality. One reason is that we know, and this is work in macaque monkey cortex, that this particular part of the brain has connections to all other major cortical areas. So that means it's really a hub in the connectivity profile of cortical parts of the brain. And that, of course, is crucial if you want to unify information that's retrieved from multiple or represented in multiple areas of the neocortex, consolidated in neocortical consolidated areas. You need to be able to, if you need to be able to unify that, that means there has to be connectivity between this part of the brain and all the major other stations. And the second component is that we know that prefrontal cortex, neurons in prefrontal cortex are important in temporal integration. And that is crucial in the sense that the binding problem in language is indifferent than the binding problems in vision, where you have to combine information that's represented in different parts of visual cortex, for instance, color and motion and object aspects. They are concurrently available and have to be combined by combining information that's spatially distributed. In speech, the situation is that information is temporally distributed. So if we understand or produce a sentence, the subject of that sentence has to agree in number with the verb phrase later on, and that information therefore still has to be available when that information comes in. And this requires a kind of working memory component that's provided by neurons in prefrontal cortex. That is what we know from, for instance, work in macaque or monkey, where delayed match to sample. So when you give the monkey a particular like object and it has to make a selection between what it has seen before, then once the object presented is taken away from the screen, and the delay time before the monkey has to answer, we see the neurons start to become very active to maintain that information online in the delay period in order to make the right selection later on. So that exactly is the kind of neuronal contributions that these neurons provide in prefrontal cortex. That's also important in solving the binding problem in language. And that's why I believe these are neurobiological reasons why part of prefrontal cortex might be playing a crucial role in the unification. Now, this is the recent book by Ray Jackanoff and Jenny Ordering, just came out like a few in this year, not too long ago, where they also argue that unification is domain general. So this combinatorial procedure is instantiated across multiple aspects of grammar, where the differentiation lies in the declarative templates, the templates for phonological structures, for syntactic structures, and for conceptual structures. These specify what needs to be combined, but the unification, like operations themselves, are not specific to these particular domains, but can be instantiated in connection to the specific domains of knowledge that needs to be unified. So it's a plausible combinatorial principle, even not only for linguistic structure, but also for a variety of other cognitive domains. And therefore they write, given this cross-faculty generality, we conclude that the relative complexity of unification is a matter to be accounted for with respect to the mind as a whole, not just in the language faculty per se. What makes language special is not so much its means for combining units as the content of what it is that's combined, phonological, syntactic, and semantic structures, rather than, say, visual or haptic representations. So in short, then, schemas plus unification, and the schemas are the information that's stored in memory that need to be unified in order to make these larger structures. Schemas plus unification can play the role usually assigned to procedural rules, namely building novel structures from stored parts. Now, in a recent paper, I've argued that multiple brain network contributions will not be language specific, but shared with other cognitive functions. Elementary linguistic units will almost certainly be domain specific. So these are the kind of the schemas that Jackanoff and Ordering refer to. But some key aspects of the elementary linguistic operations, such as unification, these might well be shared with other domains, such as music and arithmetic. So this is very similar to the view that that Jackanoff and Ordering propose. And of course, I'm happy that my let's say proposal in this context also has the backing of a very influential linguist, in this particular case, Ray Jackanoff. So here is then what you could consider to be these building blocks and the operation of unification. Let's look at this for the situation of templates or schemas in terms of syntax. So the idea then is, and this is based on the tree adjoining grammar work by Arvind Joshi, and also the treelets that Kulikov and Jackanoff have proposed, as well as the computational instantiations by Vosse and Kempen that accounted for quite a bit of behavioral data when you do the following. The idea is that anytime a particular word form comes in, like the, and this happens incrementally, it doesn't only activate its orthographic or phonological characteristics and its possible conceptual specifications, but also a small schema that specifies the local syntactic environment in which that particular word can operate. So for instance, in the case of woman, that's the head of a noun phrase, and it specifies that it's usually preceded by a determiner phrase and a prepositional phrase as a modifier of that particular element, which then collectively forms a noun phrase. And likewise, this is the case for when the verb comes in, a kind of schema for the local environment of that verb is co-activated as well. These schemas then have to be unified to get to a full phrasal configuration by matching roots and footnotes, provided that the diacritic features, like for instance, the number information matches. And in this way, unifying these elements that are retrieved from memory, one can build up by unification operations a full phrasal configuration. And therefore, the idea then is that, and for this, I refer to a paper and a study that very nicely found supportive evidence for this particular idea, that these templates, these schemas, these small syntactic schemas are retrieved from middle temporal gyrus. That's where they, in one form or another, are represented. And they are unified in dynamic interaction between parts of Broca's area and middle temporal gyrus, such that these templates are then unified on the fly, resulting in fuller phrasal configurations. Now, if you look into meta-analyses of large numbers of studies that have looked into imaging, fMRI, and likewise PET and so on, you find a gradient in inferior frontal cortex. This is an activation from an artificial grammar learning study, where it's the case that semantic information is provided or activating more the ventral part of like prefrontal cortex. Brodmann's area 47, Brodmann's area 44 and 45 are strongly activated by syntactic operations, and phonological studies find often Brodmann's area 44 and ventral part of Brodmann's area 6 activated. So it's a gradient, it's partly overlapping, but it's a gradient of activations. Now, you can do resting state connectivity analysis, where we find that the brain shows intrinsic oscillations at multiple time scales. That is, here you see the time course of a bold time series in any given part of the brain. And if you seed this particular like temporal profile and look at which other voxels in the brain correlate strongly with this, with the temporal profile in a particular seed region, you will find that especially those areas that are functionally connected have a very high correlation in terms of the temporal profile of the bold signal. And this allows you to do the following. So that is then an indication of the functional connectivity between areas that are in this way correlated in terms of their slow oscillations. So we seeded from these three different gradients of frontal cortex the time courses during a resting state, where subjects don't have to do anything in particular, but still you can find functional connectivity profiles in this particular way. We seeded the time courses of these three different regions in frontal cortex and looked which other areas in the brain show the strongest correlations with these three seeds. And then you find a very interesting pattern. You find that areas that are known to be involved in semantic processing, such as, for instance, posterior inferior temporal gyrus, angular gyrus, are strongly connected to the pars orbitalis, so the ventral part. Areas involved in syntactic processing are strongly connected to, for instance, this area that's known to be involved in syntactic processing in a temporal cortex, and likewise phonological areas in posterior temporal cortex are strongly connected to the more dorsal part, and likewise for the parietal cortex. And this has been found again in the largest, has been replicated in the human conectome project by Beckman and others, where they tested this particular idea in 470 subjects, finding the same gradients that we have found before. This then results in the idea that in the left hemisphere, but not in the right, because there we didn't find this particular topographic organization. A topographic organization is found in which areas in frontal, parietal, and temporal cortex are connected according to information type: semantic, syntactic, and phonological. So these dynamic networks then contribute very likely to the information exchange that's needed in order to retrieve and unify the information relevant for language processing. So let's zoom in now on one particular aspect, namely semantic unification. And this we can do also in its more dynamic component by looking at EEG or MEG signals when subjects are presented with sentences like "the pizza was too hot to," either ending in a expected continuation "eat" or with a word that deviates semantically from the context. If you do this, and that's of course the discovery by Martha Kutis and Steve Hilliard in the 1980s, you find a negative going voltage deflection roughly after 250 milliseconds, peaking at roughly 400 milliseconds, indicating the degree of match or mismatch between the lexical meaning of this particular word and the meaning of the context. The stronger the deviation, the larger the amplitude. This we did ourselves in a study where we had sentences that were correct, Dutch trains are yellow and very crowded, or deviated either in terms of a world knowledge violation, white is a predicate that can apply to the stuff to trains, but it so happens that such trains are yellow and not white. Or what we call the semantic violation, where the predicate is not so easy to apply to the stuff that trains are made of. If you do this, and this is Dutch train to make you believe that it's indeed not white but yellow, then what we find is that both to the world knowledge violation and the semantic violation, you get this huge negative voltage deflection starting roughly 250 milliseconds after this particular word came on the screen, and having a maximal amplitude at 400 milliseconds. And this particular effect is most strongly found if you do the fMRI version in left frontal cortex Broadman's area 47 that we've seen before. And these are 3 slices, the axial, the coronal, and the lateral slice, all the same activation, showing that it's limited or specifically found in that particular area of the brain. And likewise, you can do the MEG version of this, where we find the correct condition, the violation, and the difference is the net effect in the MEG signal, indicating this particular lateralized finding for the N400 component in its MEG aspect. Now, this can then be used in order to test 2 different accounts of semantic unification. One is what's often called strict compositionality, and that's very strongly dependent on the idea that syntax is the core feature that allows us to combine and derive complex meaning out of the building blocks of the individual words, where the meaning of an expression is claimed to be a function of the meaning of its parts and the way they are syntactically combined. An alternative account is that, because that would say that first you have to compute the meaning of a sentence, and then you can confront it with other information that you might have available as well. A situation model account, however, is the idea that linguistic expressions are processing instructions to generate a mental representation of the situation that's being described. And in that case, other information that might be available in addition to the linguistic information might also be helpful in order to constrain the interpretation space. We have tested these accounts in a large series of studies, only one of which I'm going to refer to. And this is how we integrate the knowledge of the linguistic elements themselves with the knowledge about the speaker. So for instance, if you hear the sentence, "I think I'm pregnant because I feel sick every morning," you need to relate the individual word meanings to each other, but at some point also to our knowledge of the speaker, such that you won't be surprised if this person produces this particular utterance. "I think I'm pregnant because I feel sick every morning." You might be a bit more surprised if it's coming from the mouth of this person, and you might be highly surprised if this person produces that particular utterance. So now what we did is we used the voice of the speaker, not pictures or anything else, the voice of the speaker, because the voice of the speaker also gives away information about the speaker that produces the utterance. And let me give one example. So for instance, if you hear the sentence, "On Sunday, I always get pocket money from my parents," then at the word pocket money, it might be the case that you might not be so surprised if this person produces that sentence or that utterance. You might be somewhat more surprised if a person of 40 years old is still dependent on the pocket money from his parents. I'll let you hear the sentence so that it's in Dutch, but so that you get like the feeling.
Op zondag krijg ik altijd zakgeld van mijn ouders.
Here the elder person.
Op zondag krijg ik altijd zakgeld van mijn ouders.
And of course we do all this very well balanced and controlled. So here the reversed version.
Morgen ga ik met mijn vrouw in het bos wandelen.
Sorry, this is the one that's deviant. So morgen ga ik if a child says morgen ga ik met mijn vrouw in het bos wandelen, tomorrow I'm going to make a walk with my wife in the woods. That's what you expect from this person, but not from this person.
Morgen ga ik met mijn vrouw in het bos wandelen.
Okay, so now these are all the same lexical elements, the same syntactic structure, the same semantic ingredients. But what we find is immediately after the onset, very early after the onset of the word that mismatches in the context of the expectations that you have about the particular person. So this is now the same word, but spoken by a person for which you expect this word to fit, sorry, this one, or not expect, or where you detect a mismatch between the expectation of what the content and the speaker, you immediately find the same N400 effect with exactly the same latency profile that we find when there is a language internal semantic unexpectancy, indicating that it's not the case that you compute sentence meaning and then you confront this with other information like gestures or information about the speaker. This all immediately is taken on board in constraining an interpretation space of the utterance. And again, we find exactly the same Brodmann's area 47 in left inferior frontal cortex that we've seen before as an area that seems to be recruited more strongly when it's harder to integrate that particular element of the interpretation space in your situation model than the situation where it matches your expectation. For reasons of time, I'm going to skip this particular thing. I refer to a study that we have done also where we collected information from a large number of subjects, MEG, fMRI, because we wanted to know what is domain independent, that is domain independent unification and retrieval operations that are independent of whether the input is spoken or written, so when you read or when you listen, for which we also have looked into, we collected the genetics of these subjects and also some diffusion tensor imaging resting state data and so on, where 360 cents were created that varied in syntactic complexity, where subjects were presented 120 cents in the MEG system and 60 in MRI scanner. So both subjects participated in both MRI and MEG, and where the sentences were contrasted with the same words, but now like randomized such that they created word lists that had no syntactic or semantically coherent structure. This is the MEG version of this. And then you can see both, this is part of the data set. Now we look at reading. You can see that activation starts in occipital cortex going forward to the temporal frontal cortices, both for words in a sentence and words in a list. And if you contrast this, you see the increased activation of the same words in a sentence context after a certain period of time. And this gives a picture of the real dynamics. Now we look at the dynamics of a particular word in mid-sentence position, independent of whether it's written or whether you listen to that word. So we masked away the modality specific components. And then what you see here, this is now like a slow motion type movie, where you can see the time here. And you see activation reverberating between temporal and frontal cortex. So it's not a strictly feed-forward only dynamics, but you see reverberating activity between these two parts of the brain. So if you look at the MEG signal, then what you find is that if you look at the MEG signal, you find it first after 150 or so milliseconds peak in the MEG activity in occipital cortex, followed by a peak in after 250 milliseconds in left posterior temporal cortex, which is stronger for the sentences than for the words. And then after 400 milliseconds, you see two peaks, one again in left posterior temporal cortex, so the second peak, and one in left inferior frontal cortex. And the interesting thing is that only these two peaks, the second peak, they start to highly correlate. These are the subjects, and this is the strength of the MEG response for these sentence conditions. You see the strong co-modulation between the second peak in left posterior temporal cortex and left inferior frontal cortex, indicating a dynamic interaction between these two areas around that time frame in order to unify, that's at least our idea, unify information that's retrieved from left posterior temporal cortex and then bound together with the help of left inferior frontal cortex unification contributions. this data set is available for everyone. So if you want to use these data yourself, you can download them. Here is all the methods are published in Nature Scientific Data. You can also find how to download the data from these 204 subjects, and everyone can then use that data set in order to ask your own questions and extract your own types of information from it. So an intermediate summary: the connectivity of the language cortex and left perisylvian regions is much more extended than proposed in the classical model and is not restricted to the arcuate fasciculus. The distribution of labor between the core regions in left perisylvian cortex is fundamentally different than proposed in the classical model. We found, and I have no time to discuss this in much detail, but there is shared circuitry for core aspects of language production and comprehension. It's not the case that Broca's area is for production and Wernicke's area is for comprehension. Both areas contribute to production and comprehension, which both recruit temporal parietal regions for the retrieval of linguistic information that's laid down in memory during acquisition, and unification of building blocks into utterances or interpretations that are constructed online that you can't retrieve from memory. That means that unification enables words to cooperate to form new meanings, to quote Noack. Language and other cognitive functions are neuronally implemented in dynamic networks of brain regions. And if you want to identify the role of any given region, we can only do this in the context of a larger network in which it's embedded. So it doesn't make sense to say the function of Broca's area or the function of Wernicke's area is this or that. It depends on its contribution in any given larger network, and it is found also that a node in a larger network can have different contributions dependent on the co-modulation of the network in which it's embedded. And moreover, we know that specific regions can also have different contributions at different moments in time. So in fact, what we should do, we don't do this, I also don't do this often, but I think we should go in a direction where for any specific region, we should rather speak of its functional contribution in the context of network N at time slice t. So we have to timestamp it, and we have to stamp it spatially in the context of a larger network if we want to identify a particular functional contribution of a specific region. Now, finally, in the last 5 or so minutes, I want to go beyond the core language network, namely from language to communication. And this is where I would like to address an issue that is related to the mirror neurons and sensory motor simulation. Because there has been, and especially also in the embodied framework of language processing, an idea that is originating from the finding of the mirror neurons, where the mirror neurons are found by this particular man, Giacomo Rizzolatti, who discovered that if the monkey makes a grasping movement, certain neurons in this area of the monkey cortex are strongly activated. But they, by accident, also found that the same neurons start to fire when not the monkey itself is making that grasping movement, but when the experimenter is making the grasping movement. And this resulted in the idea, and this is in an influential paper by Rizzolatti and Sinigaglia, that what these mirror neurons do, they allow the observer to understand directly the goal of the action of others. Observing actions performed by another individual elicits motor activation in the brain of the observer, similar to that which occurs when the observer planned their own actions. And the similarity between these two activations allows the observer to understand the actions of others, and this is crucial, without needing inferential processing. So by just simulating the action that the other person is making in your own brain, you are able to understand its meaning. And this, in the language field, has been made very popular by Friedemann Pulvermüller, who makes the Hebbian cell assembly argument that if you, for instance, read or see the word kick, you understand this by simulating the action of kicking that's related to that particular verb, and thereby understand its meaning. Now, the question is, will this work? And here I have a small dialogue to offer This is a famous Dutch soccer trainer, Guus Hiddink, who, let's assume, visits his sister Mien, and this is the Mien's room where they're sitting having nice coffee, where Guus says, Mien, it's warm here. And let's assume Mien version 1 answers. Mien runs her sensory like temperature neurons in the brain, which we know to be somewhere in midbrain. Indeed, Guus, it's 33 degrees. The simulation has worked, she has understood it, and she answers in confirmatory sense. However, the second Mien Hiddink 2, says something completely different. Indeed, Guus, I will open the window. And most people will find the second answer more accurate and more adequate. And the reason is that although Guus has made a statement, in fact, the listener, in this case Mien, has interpreted the statement as a request to do something about it. So the statement is interpreted as a request to do something about it, open the window or turn down the heating system. And this, of course, is what's often the case in language. Now, Rizzolatti et al. Assume that understanding language is based on sensory motor simulations, but sensory motor simulations are reenactments of coded meaning, so the reenactments of the propositional content in terms of its sensory motor aspects, but not of the speaker meaning, not of what we infer the speaker wants to convey by the statement or the utterance. So, for instance, and of course, if understanding is related to deriving speaker meaning, as Grice and others have argued, then sensory motor simulation is not good enough. So, for instance, if it's very hot here in the context of this particular environment, additional inferential steps are necessary to infer what the speaker wants to convey. Now, of course, one can say that's all arguments on theoretical grounds. But what do we find when we test this out in our neuroimaging context? And this is what one of my former PhD students, Jana Bastnakova, did, and we have done another whole series of other studies as well, but I'll give you one example. So if I ask you, did you like my presentation? One possible answer is, no, I didn't. But you could also say, it's hard to give a good presentation as an answer. It boils down to the same answer, but of course, this requires pragmatic enrichment, because it's not a direct reply, it's an indirect reply where you have to make inferences about what is the intended message that the speaker wants to convey. So what we did then, we did a study in which the very same answer was in one condition a direct reply and the other condition indirect reply. And so here assume you're now a subject in the scanner. First, you received auditorily a context and then a dialogue, and we had not less than 80 dialogue pairs, such that it really sounded very, very natural. So let's take the direct reply condition. The context you hear is the following. John needs to earn some extra course points. One of the possibilities is to attend a student conference. He's never been to a conference before, and he has to decide whether he wants to present a poster or give a 15-minute oral presentation. He's talking to his friend Robert, who has more experience with conferences. John knows that Robert will be realistic about how much work it takes to prepare a conference. And now we hear a dialogue. John, how is it to prepare a poster? Robert, a nice poster is not so easy to prepare. John, and how about a presentation? It's hard to give a good presentation. So this is the direct reply condition. Now the very same utterance is preceded by an indirect reply context. The context is as follows. John and Robert are following a course in philosophy. It's the last lesson of the semester and everybody had to turn in their assignments. Some people have written a paper and others have given a presentation about a philosopher of their choice. John has chosen the latter. When the lesson is over, he's talking to Robert. Dialogue. John, I'm relieved it's over. Robert, yes, the lecturer was really strict. John, did you find my presentation convincing? Robert, it's hard to give a good presentation. So now we looked at which neural networks, or which parts of the brain show increased activation when the very same reply is indirect rather than direct. So indirect versus direct conditions. Is this the theory of mind network, or is this areas that are related to the mirror neuron system? And in fact, the answer is very clear. Medial frontal cortex and temporal parietal junction are the areas, and these are the core nodes in the theory of mind network, are more strongly activated in the case when the same utterance is an indirect reply than when it's a direct reply. And there is an empathy-related area in anterior incipit that is co-activated as well. So in conclusion then, theory of mind areas are involved in grasping speaker meaning. The putative mirror neuron system and motor simulation is not sufficient for understanding the intended message of the speaker. Listeners take the speaker's perspective at both the cognitive and affective levels, and this seems to be crucial to infer speaker meaning. So to conclude then, what I've tried to show you is that if we look at this complex function of language and its neurobiological underpinnings, we have to identify the contributions of multiple networks that collectively will take on board all of the complex components that it instantiates. So left temporal, frontal, parietal areas are, you could say, are part of what you could call the core linguistic machinery, memory, unification, and control. For the construction of a situation model, I've not shown the data, but we found that also if you include these utterances in larger discourses and build up a situation model that spans multiple utterances, you find right inferior frontal cortex contributions as well. And if you want to infer and derive speaker meaning and communication, both in production and comprehension, I've not shown the production part here, then it requires medial frontal cortex and temporal parietal junction contributions also. That is the classical theory of mind network. All these different networks collectively will instantiate what's needed in order to communicate by means of language. None of them in isolation will do all of the work, but of course we have to decompose the system in its components and try to assign and contribute the functionality of each of these networks to get a handle on how this particular complex function is neurobiologically instantiated. And with this, I would like to thank you for your attention.
Okay, thank you so much, Peter. Normally at this point we hear applause from different rooms around the world. We of course now we can't hear that. So let's just assume that people are applauding you online in isolation.
In isolation.
So thank you. Can you see the chat box?
Can I see the chat box? I see. Thank you for a great talk. I see someone saying.
If you scroll up, you should first see a question from Greg Hickok.
I don't see Greg Hickok's question, but maybe you can.
Okay.
Let's see chat.
I can read it out to you if you don't see it.
Okay, fine. Let's see it.
I think that's the first question. Yes. So this is a question by Greg Hickok. It's your notion of unification appears to apply symmetrically to receptive and expressive aspects of sentence processing. You link this operation to IFG roughly, and cited early evidence from Karamazov and Zhurev as lesion support. Yet modern lesion evidence suggests asymmetrical involvement of IFG versus posterior temporal lobe. Frontal is implicated predominantly in expression, whereas temporal is implicated in both expression and comprehension. Are you willing to revise your model in light of this new evidence?
Well, the question then is, what is the evidence? So of course we and others as well work by the Tyler lab and also the Leipzig lab. Every time we do studies of language processing beyond single words, we find, in comprehension that is, we find always inferior frontal cortex involvement activations as well. So the question then is if this particular, I mean, of course, there is a difference in the sense that often in production you can't bypass certain operations that you can bypass in comprehension. So in that sense, the necessity to recruit these different operations and like information structures that need to be recruited can be differentially recruited in comprehension and production. But I don't think there's firm evidence that Broca's area is only there for production and not for comprehension, because that is at odds with all the findings that we have all the time, where we find activations in frontal cortex as well for comprehension and production. So I don't know exactly whether the asymmetry that Greg is reporting, how serious this is in terms of the fact that let's say Broca's area is only contributing to production and not to comprehension. That I would not necessarily feel supported by the data. A certain asymmetry can be the differential recruitment in production and comprehension as a result of the additional information that's available in one case, comprehension, that's not there in the other case, production.
I think we have a follow-up from William Matchen asking to use his mic. So please go ahead, William.
Can you hear me okay?
Yes.
Yeah.
Okay. Hi, Peter, this is William Matchen. So just to follow up for Greg here, I think, so what we reviewed, that we just published this paper in cerebral cortex, and so we agree, at least I pretty strongly agree with you, that the neuroimaging data show pretty tight correspondence between activation in Broca's area and the posterior temporal lobe. But then if you look at aphasia, you definitely see very strong differences if you at a first blush between, let's say, fluent and non-fluent aphasia with respect to posterior temporal and inferior frontal damage respectively. And then if you look in more detail, you see very severe sentence comprehension deficits in posterior temporal damage, but not so much with frontal damage, and maybe in some circumstances where you've had like a particularly difficult task or construction. And then you see like the same thing with acceptability judgments. So there's that nice paper, lesion symptom mapping work by Stephen Wilson and Sagan that showed basically that posterior temporal damage, you get strong acceptability judgment deficits for syntactic constructions and not so much inferior frontal. And then finally, we are just about to publish this work on paragrammatism and agrammatism, and they doubly dissociate with respect to posterior temporal and inferior frontal damage. So I think that's what Greg would say is the neuroimaging data are mostly equivocal, but then when you look at aphasia, you see these really strong dissociations.
Yeah, but the question is a bit, I mean, of course, let's say we see more things where not always the lesion data and the neuroimaging data are exactly in line. Also, of course, because the lesion data are not necessarily very neatly taking the borders of areas that might be functionally relevant, because they're, as Spoke already said in the past, they're an artifact of the vascularization of the brain. So that makes it harder to have neat functional borders there. But the other thing is that, and because I've done aphasia work myself in the past for a long time, and clearly, of course, what's the case in comprehension in patients is that they can, so there is enough stuff to do good enough processing and bypass the fact that you don't need to build a full phrasal configuration in order to still get at an interpretation that in the light of additional knowledge that you have or contextual information that you have makes sense. So for instance, any permutation of the words apple, man, eat will result in the correct interpretation by the patient, because it doesn't require syntactic knowledge in order to infer that particular meaning. This is different in production. In production, you can't bypass, let's say, syntactic encoding in order to produce a well-formed sentence. So in essence, there is more bypass possibilities maybe in comprehension than in production. And my question is a bit, isn't that part of the difference that you might find between these two cases if you take that particular these particular issues into consideration. That doesn't mean necessarily that they are functionally completely different in comprehension and production, but the recruitment of the different steps and the different operations and knowledge types that is there in production and comprehension might result in this seeming discrepancy.
Yeah, I mean, just a brief follow-up though, I agree that, like, you know, we have to look at each of these particular tasks and very carefully assess to what extent the task requires that. So I totally agree on that point. Just to maybe if you could comment very briefly on what about the dissociation between paragrammatism and agrammatism, where these things look different and they doubly dissociate with respect to posterior and inferior frontal damage.
Yeah, that, I mean, then I need to see the data more detail to give any sensible comment, because let's say because it's also not clear to me from your point of view what would then be the difference, because both paragrammatism and agrammatisms are dependent on the syntactic machinery to some degree, and if the one aspect of syntactic machinery is posterior, the other aspect of the syntactic machinery is more in frontal cortex, then still it's not clear to me what's the model of syntactic, underlying model of syntactic processing that you assume to be there in order to account for these data. So one of the things that I think is crucial in this particular case, and that's why I made this very specific model based on Aravind Yoshi, I have the feeling that in many ways we talk about comprehension and production when it comes to syntax without a very explicit idea about that, how that's computationally instantiated. What are the kind of key elements that might be retrieved in a lexical syntactic notion? How are they combined? Unless you have a specification of that particular computational machinery, it's very hard to say, well, I look at agrammatic construction and paragrammatic constructions and I find a dissociation, then still the answer is not given. What are the contributions of these different areas such that this is the outcome? And then, of course, we then need to be seen specified in terms of an underlying computational model of syntactic processing.
Well, yeah, I totally agree on that point. I'll just finish. I think maybe we can discuss this more at another time. But I would really love to hear your feedback on the paper that I just published with Greg Hickok, Matching Hickok 2019 Cerebral Cortex. We kind of lay out the model, and I agree with you. I really like the kind of lexicalized syntactic structures that you've been advocating for such a long time. But we're going to be publishing that work in Paragram soon, and I would love to hear your feedback on that as well at some point.
Just send me the paper, and I will come back to you.
Thank you so much. Appreciate that.
Okay.
Thank you. We have another question as well online from Ikan Seko, which is an intriguing online name. I don't know who goes behind the name, but we often hear that language is acquired normally by anyone healthy. Are there any components of your model that can differ with things such as IQ, a theory of mind?
Let's say, lo and behold, all healthy infants and members of our species without any formal instruction acquire a spoken language capacity. And of course, there might be, let's say, individual differences in the vocabulary, the size of the vocabulary that they acquire. There might be individual differences in terms of how many languages they are able to learn. So there are certainly individual differences in these skills, but the basic skills we all acquire. And the interesting thing is, and that's actually in our institute, Antje Meijer and her group are looking into individual differences in the normal language skills, because in fact, for healthy participants, we lack basic insight into how much of individual variation there is. That's what we clearly need to figure out more. But I think the basic architecture will be shared. And in terms of the theory of mind network, clearly there we see that, for instance, patients with autistic spectrum disorder they will very much have the likelihood of failing on the pragmatic interpretation of these utterances in context. So they take often the propositional content literally and have a harder time in figuring out what is the speaker meaning, what's the intended message that the speaker wants to convey with this utterance. So that's let's say when there are failures of these systems, of course, like theory of mind, or when there is dyslexia, then of course there will be the reading system will be impaired and so on and so forth. But the idea is that the basic architecture is very likely shared, but of course the individual variability could be linked to size of working memory needed for language and executive control operations that need to be in place in order to monitor what's going on with the linguistic operations themselves. And as I said, very little information about the individual variability in the healthy population is there. And that's something where we're working on, but for which answers are still outstanding.
Thank you. And the question was from Enriqueta Canseco Gonzalez from Reed College. Okay, we have a question from Julius Fredrickson, which I'll read out. Thank you, Peter. This was a wonderful lecture. I have a question regarding the role of domain general areas in language processing, for example, in relation to unification. In several papers, F. Fedorenko and colleagues have revealed very convincing evidence for language-specific regions which, by and large, are responsible for language processing, but with minimal contribution of domain general areas. Regarding the areas you consider as being crucial for unification, do you think subregions within those broader areas are crucial for language-specific unification, or are unification areas truly domain general?
So the view that I hold is that, and as you've seen in the gradient, the domain specificity of the unification is not so much dependent on the inferior frontal cortex itself, but is the interaction between the domain specific knowledge domains that need to be unified in connection to parts of the frontal cortex to which it's most strongly connected. So it's the connectivity profile between parts of frontal cortex, parts of Broca's area, and temporal parietal areas that deliver the domain specific information that will create the, let's say, language related unification specificity. But that's more to do with the fact of how these parts of frontal cortex are connected, rather than that they are necessarily dependent on a particular part of frontal cortex. And this goes very much in the light of, in line with, I mean, Marina Bettany and others have shown that even occipital cortex can be recruited for high-level language functions if the usual information is not provided that particular part of the brain, in the congenitally blind. So it's the case that it's very strongly dependent on the connectivity profiles, what the contribution of any given area is going to be in this context, rather than that every subpart of Broca's area, cytoarchitectonically or receptor architectonically or myelino-architectonically, can only do one particular thing. So that particular thing here is that the unification operations there, I share the view that Ray Jackanoff holds, is very strongly dependent on the fact that these operations are instantiated in connection to domain-specific knowledge. That's also why another finding can be then explained, because like work by William Master Wilson and others also clearly shows that Broca's area is involved in inflectional morphology. So where we have to decompose at the word level, like the stem and affix and so on, or suffix. And that's again something different than phrasal syntax, and nevertheless we find overlapping activations in that particular part of the brain. So that means that very likely again there it's what it gets delivered and how that's connected to the domain specific knowledge areas in temporal parietal cortex is what's going to be determining the contribution of that particular area in terms of unification. It's a long winding sentence, but I hope I got my point across.
Okay, thank you. We have another question, Valerie Yi. New evidence shows that the hippocampus, which is not usually included in language models, plays a role in language processing. What is your take on the role of the hippocampus in language processing? Should we consider the hippocampus in language models?
I think we should, although it's to me not completely clear. Let's say what its contribution is. We, for instance, know in the studies of HM and so on, this is already work that has been published a long time ago, that HM had very little problems in language processing and discourse processing. And it's also the case that patients with hippocampal problems are often, for instance, they have subtle problems like pronoun co-referential relations are harder and so on, but core operations such as word recognition and syntactic combinatorial operations and so on, they seem usually to do fine. Of course, it might play a role in language learning, so learning new words and learning new items in language might initially be hippocampal dependent, and later on can be consolidated in neocortical structures. So I think in language learning, or maybe building up larger situation models of utterances spanning multiple discourses spanning multiple utterances, it might play a role. But again, I think we need to do a bit more research in order to figure out exactly what the hippocampal contribution is. Likewise, I think we need to look at subcortical structures such as the basal ganglia, the cerebellar thalamo-basal ganglia circuitry will absolutely crucially be involved in the temporal sequencing of information in articulation, for instance. So clearly, it's one thing to retrieve information from memory, but at the end, but it's another thing to sequence this in a series of speech sounds that have to be produced. And for that particular thing, for that particular sequencing process, very likely or almost certainly subcortical structures such as the basal ganglia and the cerebellum will play a crucial role as well. So we should indeed look also in areas beyond what we've seen so far, which are mostly cortical nodes in the network. But the subcortical aspects, we should also try to investigate more.
We have another question from William Machen. Syntax is how things, for example, words or phrases, are put together. So is it contradictory to say that what's special about language isn't how things are put together, but that it's putting together syntactic things?
Say that again.
So the question is whether it would be controversial to say that what is special about language isn't how things are put together, so an emphasis on the process itself, but the fact that it's putting together syntactic things. Is that what is special about language?
Well, again, I mean, I think putting together, let's say things like morphemes or inflection, compose words from different components. That's also putting things together. We're putting sounds together in syllabic frames and so on. So all these things, I guess, are partly like unique to humans, and that thing, it's not clear to me that only syntax in that context is the unique contribution. Because what makes the unique contribution of the human language system is the fact that we connect these three levels, these phonology, syntax, and semantics, and that we don't see in any other species. We can look at species like, and we can look at songbirds, we can look at sequencing in non-human primates. But the fact that we that these interfaces of syntax, semantics, and phonology happens, that these three levels and these three layers, I consider to be the uniquely human component of the language system, rather than any one in of itself. And we might see, of course, complexity difference between human species and other species, but we very likely will also find precursors that can be found in other species. But the total package will make it unique.
Peter, I think this is a good moment to end our session. You've dealt with so many questions already. Thank you so much for a wonderful talk and for giving your time in the late hours in the Netherlands. And I want to compliment you on the atmospheric lighting of your office as well at home.
Yes, it starts to get darker here. It's a bit of a funny, I mean, it's unusual also for me to speak to my own screen and don't see the audience and so on. So it's somewhat more complex than when I have direct interactions with an audience. But I guess that this we have to get used to anyway in the current circumstances. So in that sense, I thank all of you for being there and listening and asking your questions. And let me end with wishing you all the best in the current circumstances. Keep yourself, health and safety. And hopefully then once we get over with this whole corona crisis, we will be able to meet again in one form or another at a conference or at the bar.